Welcome back to this series, where I teach you how compilers work. If you didn't get caught up on the last episode, then what are you doing? Go watch that first, nerd. But if you've seen it, then today, I'll be going into how to declare and use variables, explain some more stuff, and get really technical. I realized that last time, I made a few mistakes. And the first thing I'd like to touch on is that I told you that registers are 8 bytes, but that the exit codes are 1 byte. So then you may be asking yourself, why am I using an 8-byte register for a job that requires only 1 byte? Well, here's your answer. In x86, registers are 8 bytes, but there are mini registers that are just smaller parts of the big one. For example, the register used for describing syscalls, which is RAX, has multiple mini registers. The first 32 bits are stored in EAX, the first 16 in AX, and the first 8 in AL. AL, AX, and EAX are all using the same data that are stored in racks, but they simply possess less of the total data. In Linux, when you move the number 9 into RDI for the exit code, the kernel is actually reading the smallest 8 bits stored in RDI as the exit code rather than the entire 8 bytes. I hope that made sense to you. Don't worry if it didn't though. It's totally unrelated to what we'll be doing today. What we will have by the end of this episode is a way to declare variables, set values to them, and read their values for later. So let's get started with that. The first step of making a variable declaration is by adding it to the parser. In the last episode, I didn't show you how to make one because they're a little too complicated for an introductory episode to a series mainly focused on assembly. However, I hope by watching other people's tutorials or simply messing around, you manage to get variable declarations parsing. But now that you have that, we can finally get into the fun part, the assembly. If we imagine that a variable declaration is a statement that has a string for the name and an expression for the value, then we will start by generating the expression. Before we do that though, you must check if no other variable with that name exists. Create a table, map, or whatever your language is equivalent and have a key of string and a value of an integer. You'll see why later. Check if the name of the variable we are declaring is already in the map. If so, write a custom error message. If not, we can continue and generate the expression. Because the only expression we have implemented at the moment is integer literals, this will be pushing an integer literal to the stack. I breezed past what the stack does in the previous episode, but I think I need some time to explain it further. The stack is a chunk of memory that lives in RAM and is easily accessible to your code. Pretty much anything can be stored here, including our integer literals and our variables. The stack is often confused with the heap, but they are completely different. Pretty much the only thing they have in common is that they store data in RAM. The heap is what is called dynamic memory, where the kernel supplies you pages of memory upon request. The stack, however, is already given to you and automatically allocates more memory at runtime. The stack is made up of only 2 actually important operations, pushing and popping. If you imagine the stack is like a stack of papers or pancakes, then the only place where data is available is the top. This is the way that pushing and popping values work too. All stack operations occur on the top of the stack, either adding more pancakes or removing pancakes. Pushing will create a new one, and popping will remove the last one. Additionally, in x86 we have what is called the stack pointer. The stack pointer is a register that always points to the most recently pushed item on the stack. When you push something RSP, the stack pointer decreases. The stack grows upwards in memory, and popping will increase it. Because the stack pointer is, well, a pointer, you can do pointer arithmetic and get pieces of memory that aren't directly on top of the stack. You don't have to add and subtract the register manually though, as in x86 we have what are called offsets. Basically, if you put 8 RSP, that is telling the computer to access the bytes located at RSP plus 8. You can also do this with negative offsets to access memory from higher on the stack. This is where we will store all of our variables, as this will not tamper with any pre-existing data that's important. Back in our compiler, we have generated the expression, but we still need to put it somewhere. To keep track of our variables and where they are, we have created a table of strings and numbers, but we still need to create a new number variable called the variable count, or anything you want. We will insert a new entry into our table with the name of the variable and the current variable count. We will then need to pop the integer literal and place it into its final destination on the stack. We will calculate this position by using the variable count and a little bit of pointer arithmetic. In GAS, we create offsets from pointers stored in registers by using parentheses. Put the stack pointer RSP in between parentheses, and that is the current location of the stack pointer. But we want to add an offset so we don't override any memory. By adding a number before the parentheses, that makes an offset. So multiply the current variable count by -8. This is negative because we want the variable to not override any data already on the stack, and 8 because the variable is 8 bytes large. And add RSP after it, and that's your stack location. Add pop Q plus that offset, and now you have a functioning variable declaration system. But a variable is useless if you can't refer to it and use it. So the next step is to retrieve that and push it, just like we pushed the integer literal. When you encounter an identifier, aka a bunch of letters, you can assume that it is a variable. When you encounter this identifier, look up the number in the table using the identifier. If the identifier is not a key in the table, you can error and say undefined variable. If you did get a result, however, you will do basically the same calculation you did in the variable declaration statement. Multiply it by -8, add parentheses and RSP, then push it. The reason we use RBP is because in x86 it's known as the base pointer. That's where you get the BP from. This register is the reason why you typically imagine functions as individual scopes of variables. We will be using RBP here for two reasons. One is because, as I just mentioned, it can be used to create scopes of variables. The second reason is because when using a push-pop method like our compiler does, we would need to use a different offset based on how many things have been pushed on the stack. In RBP, however, we never need to change the offset of the variable. We can create a system like this by adding just a few lines of assembly code. Depending on if your language runs inside of functions, like a main or entry function in C, or runs in the global scope, like JavaScript or Python, you would add these lines of assembly to either the beginning of the program or the beginning of each function declaration. At the end of the function or scope, including returns, but not including exit statements, you would add this line of code, pop q RBP. The reason we add a push is because we want to preserve the original scope of whatever function called this function. We then move RSP into RBP, so we have a fresh pointer to the top of the function stack that we can use to add offsets for our variables. We then pop RBP so we are allowed to return to the previous scope of the function that called us. That was easier than expected, right? The best part is, since we are already using the push-pop system to store our variables, we can already create new variables equal to the value of old variables, and use those variables to exit the program. Assuming your compiler didn't error, you should be able to assemble the output, run the executable, and get 5. You can even make a variable y, set it equal to x, and then exit with y, and you should still get 5. What about adding these numbers together? Multiplying, dividing, getting their negatives? Well, you're gonna have to wait for that, because now it's time to end the video. I know this episode was pretty dense and technical, but I hope you still learned something new today. Come back soon for the next installment of Writing Our Compiler, and please subscribe so more curious people like you can see the video and learn something new themselves.